Inside your battery, there's basically a tiny, well-mannered war going on. No explosions, just atoms passive-aggressively handing off electrons like, you take it, no, you take it. And somehow, that awkward chemical breakup is what powers your phone, your car, and your questionable late-night decisions. So, what's actually happening in there? Why do electrons feel the need to travel? And how does their little drama turn into usable energy? Let's crack open the most polite battlefield in your pocket. Inside every battery is basically a very polite argument about who gets to keep the electrons. And unlike your group chat, this argument actually accomplishes something. A battery has two electrodes made of different materials, say zinc and copper, that have different appetites for electrons. Zinc is like, I guess I'll give up some electrons, while copper is like, oh, I'll absolutely take those. Thank you. This difference in personality creates a potential difference, which is just science speak for tension. And that tension is what pushes electrons through a wire when you connect the circuit. But here's the catch. Inside the battery, electrons can't just stroll directly from zinc to copper, so they're forced to take the scenic route through your device. That's your electric current. Meanwhile, inside the battery, ions are shuffling around in an electrolyte, balancing charges like a very organized mediator saying, let's keep this civil, everyone. So the whole thing is less like an explosion and more like a structured debate where electrons are quietly leaving one side, traveling through your phone to light up your screen, and arriving at the other side where they are warmly welcomed. It's chemistry doing conflict resolution so efficiently that it powers your life. If electrons could do whatever they wanted inside a battery, they'd just cut straight across and your phone would be about as useful as a decorative brick. The electrolyte exists specifically to prevent that shortcut, acting like a referee who says, no direct electron passing, take it outside. Inside the battery, the electrolyte is a chemical medium that lets ions, charged atoms, move freely between the two electrodes. When zinc gives up electrons, it turns into positively charged ions, and those ions drift into the electrolyte, like guests, leaving a party early. On the other side, the copper electrode is gaining electrons, so it needs positive ions arriving to keep things balanced. Otherwise, the whole system would just shut down from charge buildup. So the electrolyte quietly coordinates this movement, letting ions migrate while electrons are forced to travel through the external circuit. That's why your flashlight turns on instead of the battery just internally resolving its issues and going back to sleep. It's like forcing two people who are arguing to communicate only through letters sent around the entire city, and somehow those letters are powering your Spotify playlist. The electrolyte doesn't generate energy itself, it just enforces the rules of the argument, so the energy gets used in a useful way. A battery isn't storing electricity the way a water bottle stores water, it's storing the potential for a chemical transformation that just happens to shove electrons around when it occurs. Inside, atoms are constantly rearranging themselves through chemical reactions called redox reactions, short for reduction and oxidation, which sound like skincare routines but are actually about electron transfer. Oxidation is when a material loses electrons like zinc, saying, fine, take them. And reduction is when another material gains those electrons like copper, saying, don't mind if I do. Every time this exchange happens, energy is released because the electrons are moving from a higher energy situation to a lower energy one, like rolling downhill. But instead of just releasing that energy as heat or chaos, the battery channels it into a controlled flow of electrons through a circuit. So every time you check your phone, you're basically watching billions of tiny chemical rearrangements happening in sync, like a microscopic flash mob, where atoms swap partners and electrons sprint through wires. The energy you're using isn't coming from nowhere, it was locked into the chemical bonds of the battery materials, and the battery is slowly cashing that in, one polite electron disagreement at a time. When your battery dies, it hasn't run out of electrons, those are still very much present, hanging around like guests after the party has ended, it's just run out of drama. The whole system depends on a difference between the two electrodes. One wants to lose electrons, the other wants to gain them. Over time, as the chemical reactions proceed, the materials change. The zinc that was happily giving up electrons gets used up or transformed, and the copper side becomes less eager to accept more. Eventually, they reach a sort of chemical détente where neither side feels strongly enough to keep the electrons moving. The potential difference drops, the current stops, and your phone goes dark. It's like the argument has been resolved and everyone is now politely agreeing, which is great for interpersonal relationships but terrible for powering electronics. In rechargeable batteries, you can actually reverse this process by applying external energy, basically forcing the participants back into their original argumentative states so they can start the whole cycle again. But in disposable batteries, once the chemicals settle down, that's it, the argument is over. The electrons are staying put, and your remote control is left pressing buttons into the void. Voltage sounds like a serious, intimidating physics term, but it's really just a measure of how intense the electron disagreement is inside the battery. Imagine two people arguing over who gets the last slice of pizza. If one person kind of wants it and the other really wants it, that's a mild situation, low voltage. But if one person is absolutely determined and the other is equally stubborn, now you've got high voltage. In a battery, this intensity comes from the chemical properties of the electrode materials. Some combinations create a bigger difference in electron preference, which means a stronger push on the electrons when a circuit is connected. That push is what we measure as voltage. A AA battery has about 1.5 volts, meaning a modest but steady insistence, while something like a car battery brings a much more forceful, "we are moving these electrons now." But voltage alone isn't everything. You also need a pathway and the ability to sustain the reactions. Still, it's voltage that sets the tone, the urgency of the whole situation. Without it, electrons would just sit around doing nothing, like co-workers in a meeting with no agenda. With it, they're motivated to move, and that movement is what powers everything from your flashlight to your laptop. So next time you see a voltage rating, just remember, it's a number that tells you how strongly those tiny chemical participants are insisting, very politely, that the electrons change sides.